Okay, here we have a conservation of energy problem with non-conservative forces. This problem is a great example of the type of ways that we work with non-conservative forces because it involves both a downhill section and an uphill section and some great use of angles. Okay, so we have just one question here, and the question is, what is the distance that the truck moves up the ramp? All right, and the ramp has friction, so let's read the setup. We have a truck with a given mass that has a brake failure while going down an icy mountain. We are given the angle of the slope, alpha, of the mountain it is initially running away down, and we're told that the truck, before it starts to actually run down the slope, has an initial velocity of 19.5 meters per second, highway velocity. After careening downhill, and we're told that it runs away for 335 meters, and there's no friction during that section because of the icy road, the truck then steers onto a runaway vehicle ramp on the side of the road. Okay, well this runaway ramp, made of gravel likely, has a high friction coefficient and a different angle. So we're given the slope of the runaway ramp, 27. All right, steeper than the road that the truck was traveling down. And that sandy surface of the runaway ramp has a coefficient of friction, kinetic friction, quite high, that is 0.642. All right, and at some point we can talk about the fact that here we're using kinetic friction. For rolling motion, truly static friction would be the best choice if the truck was to be rolling up. But here we're going to assume that the tires are not rolling once they reach the truck ramp, and so they're just entirely skidding. Hence the coefficient of kinetic friction rather than static friction. Again, static friction being typical for rolling motion, but this problem not involving rolling motion. Okay, so let's define our energy points. All right, so our 1, 2, and 3 in this case, because we're going to have 3 points we want to consider. Okay, so this will be our point 1 here. Point 2 will be at the bottom. And then point 3 will be that maximum height reached up the ramp. Okay, all right, so let's think about energy conservation with these different stages. So we have E1 equals E2 equals E3. Okay, now not mechanical energy, total energy, because we will be losing energy to the dissipative non-conservative friction force between steps 2 and 3. All right, so let's find the velocity at the bottom. So we want to find V2. Okay, so let's write what we know about E1. So we're going to have the potential energy at 1 plus the kinetic energy at 1. Okay, no non-conservative work, and that's going to equal the potential energy at 2 and the kinetic energy at 2. Okay, we're going to define y equals 0 as the bottom of the slope before the runaway ramp starts. So then what this is going to look like, when we write it, we're going to have the mass of the truck, G, and then we're going to have a height. I'm going to call this one, because we're trying to solve for D, I believe. Yes, okay, so we're going to call this one H. All right, and what else do we have? Well, we're going to have the initial kinetic energy, which is just 1/2 mv0 squared, and then that's going to be equal to the final potential energy, which is 0, and final I mean at 0.2, and the kinetic energy at 0.2. Okay, which we'll just call v squared because that we're interested in that velocity being eaten up. But I already wrote v2 in the figure, so v2. Okay. All right, and that's eaten up by friction and gravity by the time we get here. But we're not there yet. We need to find the velocity at 2. All right, so what that's going to look like, well, we can cancel out our m's because they're in each of the terms. Okay, and it's good to be kind of cognizant of when and when you can't do that, or when you should expect to be able to cancel out the mass, and when you shouldn't expect to cancel out the mass. Always something you should be thinking of. Ideally, okay, so what this is going to look like, well, we're going to have the 2gh plus v0 squared. All right, and that's after distributing the 2, right? Basically multiplying everything by 2, and yeah, and then taking the square root. All right, so Okay, so what I'm going to do is I'm going to leave that in symbolic form so we can use it in our next step. All right. All right, so now what we want to do is consider what's happening between points 2 and 3. Okay, so to do that, we'll set up a similar equation, conservation of energy equation, potential energy at 2 plus kinetic energy at 2 plus work from non-conservative forces equals the potential energy at 3 plus the kinetic energy at 3. Okay, looks great. All right, so the potential energy at 2 we know is 0. We know the kinetic energy at 2 is 1/2 mv2 squared, and we can substitute in the expression that we just created above using the first conservation energy equation. Then we're going to have the work done by friction. So this is going to be the friction force, and then multiplied by the distance d that we're trying to solve for, and then the angle between those two vectors, which is 180 degrees. Okay? So simply what I'm saying with those vectors, if we go ahead and draw them on the figure, is that our displacement vector is like so, and our friction vector is this way. So the angle between them is 180. Okay. And then that's going to be equal to the potential energy at 3, which is going to be, okay, mg, and then I'll call this h3. Okay, just to, not that it's the third h we talked about, but just so it corresponds with the number 3, the energy point. Okay, and we want the truck to have come to a stop, so we're going to have no kinetic energy. Okay, and what is h3? So let's go ahead and show that on the figure here. All right, and well, while we're at it, we'll talk about h as well. Okay, we're going to talk about h, which, let's be consistent and call h1. All right, so we'll go ahead and draw h here on the figure. Okay, that is h. Okay, and then over here we'll draw h3. All right, and of course I should have called h1. So that's h1. Okay, so we can think about how those are related to the different angles that were given, as well as the distance that we're either given or trying to solve for, that being L and D respectively. All right, so we'll go ahead and show that over here. So we're going to have that h1 is, well, I mean, we see that the angle alpha, that would be h, so sine of alpha would be h1 over L. So that tells me then that h1 is going to be L sine theta. All right, so L sine, but alpha, I mean, not theta, because our angle is not theta, but alpha. Okay. And for h3, we have that we're trying to solve for d. So we're going to express h3, similarly in terms of d instead of L, and it should just be the same, d sine beta. And again, we can think about how beta is defined, and we can think of opposite over hypotenuse would be h3 over d. And so then we multiply both sides by d and get that h3 is d sine beta. Okay? Okay. Now let's wrap up this energy problem. Okay? We don't have too many steps left to do. Especially since we've squared away what our heights are in terms of the angles and our distances. So anyway, let's move forward, and we want to solve for D, but I want to substitute in what we know for H3 first. Okay, so, because we do see a D in the expression, but there'll be one more once we express H3. All right, so 1/2 mv2 squared, substitute that later, plus the force of friction. Oh, that's right, we do still have to deal with the force of friction, times d. All right, cosine of, well, let's deal with that cosine, put the negative here. All right, so there went our cosine 180 into a -1. And mg d sine beta. Okay, looks great. Okay, so what we want to do now is actually look at the force of friction. Because what information are we given? Well, we're given the friction coefficient. We're not told the work of friction, in which case or even the friction force itself. So we have to solve for the friction force. So we want to consider a free body diagram, which I will draw down where we're at. Okay, so this will be our slope. We're going to have the truck here, right? Just represented as a box. All right, beta is our slope. All right, and what are our force vectors? Well, we got our normal vector here. We've got the gravitational vector here, and we got the friction vector here. Okay, and so that's going to be Fg, F friction, oh, F normal, and the force of friction. And okay, so we want to define our coordinate axes, and they're going to be yeah, because we just want to yeah, so we'll set them up like this. Okay, x and y, and if we look at our forces, so okay, so all right, so yeah, and I want to make sure you can see this. Okay, there you can see the axis now. So we zoom in a bit on it. Okay, so what we need to do then is just solve for the friction force. So what we know is we have F net x is going to be Fg sine beta, and in the negative direction, and in the positive direction we have the normal force. So we have Fn. Okay, that's going to equal 0. And then we have the friction force, all right, which is going to be F net. It's going to show up F net in x. Oh, and the one above was y. Okay, and then so this is going to have two negative forces, the negative friction force, the negative gravitational force. All right, so which is going to be Fg cosine theta. All right. Oh, actually, well, let's clear that up because I got some mistakes here with our, right, because actually the components for F, G, Y, and FGX being down here are not as I express them, so they need to be fixed because this angle right here is beta. So then what we see is that the Y component is cosine. Okay, so it's cosine there, and the x component is sine. All right, so we'll double check these, cosine and sine. Okay, we'll use the definition of the friction force up here. So friction force is going to be mu k Fn. All right, clearly the truck is not moving at constant velocity, so we have ma. Okay. And it's in the negative x direction, so negative ma. Okay. All right. Looks good. But in reality, although maybe it was thorough to write out the sum of forces in the x direction, we're not going to need them to find our friction force. All right, so what I'll go ahead and write down here as our next step, it is going to be that the friction force then is going to be mu k, and then we know that Fn is simply going to be Fg cosine theta. And oh, I have a mistake here though. I said equals. In reality, it's minus. I don't know why I had an equal sign there. But then it does show that they are equal to each other. Okay, so that's a mu k mg for Fg, and then cosine beta. All right, so that's our friction force. And we can go ahead back up to our expression for energy and wrap it up. All right, and we'll move this out of the way a bit. All right, and then we're going to show that we have 1/2. All right, I'm going to go ahead and substitute in V2 since we're getting close to the final step. 2gh1 plus v naught squared. All right, and then minus the friction force, which is mu k mg cosine of beta multiplied by distance, the d we're trying to solve for, and then mg d sine beta. Okay, We then put both our d terms on the same side. So we're going to have m, or we'll factor out the d, mg sine beta plus mu k mg cosine beta is going to equal 1/2 mgh1 plus v naught squared. Okay. Okay, and I've just reorganized a bit, and now we can plug in our numbers and solve for d. So we're going to have 1/2. Let's see what is going to factor out here. Okay, so quite a big thing is the masses cancel out. All right, so they cancel out in all 4 of our terms. Okay, which, oh yeah, because I put the parenthesis in the wrong place. All right, so let's fix that. So it's 1/2 m, like so. All right, so that mass cancels out. All right, so then our expression for the distance is going to be 1/2, or we can, yeah, anyway, make it a little bit larger. So 1/2, and then gh1 plus v naught. Oh, and I actually should finally clear up h1, right, because it wasn't given. So it's vl sine alpha, and then plus v naught squared. All right, so that's our denominator. And then we have sine beta plus mu k g cosine beta. And I won't get into exactly interpreting all the terms or the ratios, but definitely it's a good idea to look at this and think about what happens as you change the values and why the values are weighted this way. Okay, let's plug in our numbers. 1/2. All right, 9.8 meters per second squared. All right, for L, we have 335 meters. 335, and then sine of alpha, which is 12, all right, plus that initial velocity of 19.5 squared, and then sine of beta, which we haven't, that's the 27.9, so 27.9. And then our friction coefficient, which was 0.642 times 9.8 meters per second squared. Hold on here. We have a missing g. So let me pull that out to the front. All right, so 0.642, and then we put in the cosine of 27.9, and then I'll just pull numbers out a bit to get our gravity term in there. All right, 9.8 meters per second squared. Okay, so I just fixed a missing 2 that we lost on the 2gh1. Okay, so that's fixed, and now we can plug in our values and find our final result here. Okay. So let's go ahead and do that on the calculator. All right, so we're going to have all in the numerator 0.5, and then times 9.8 times 335 times sine of 12 plus 19.5 squared. Okay, let's get rid of that. Okay. And then in the denominator, we'll lead with a 9.8, like we led with a 1/2 up in the numerator. And sine of 27.9. see if we got all our parentheses right here. Okay, so we get 113 meters as our final value of D. Okay, and we'll round that to 114 meters. Okay, thank you.